The purpose of this presentation is to give you some background in how to translate from ladder logic to Boolean logic. We begin by looking at the origins of ladder logic. In other words, why did it come to be as it is now? According to Wikipedia, ladder logic, or ladder diagram, was developed in the early days of programmable controllers to allow factory engineers and technicians to develop software without additional training to learn a language, such as Fortran or other general-purpose computer language. It must be kept in mind that in the early days of PLCs, few people, especially those in direct contact with industrial machinery, had access to, let alone knowledge of, the inner workings of microprocessors or computers. It was for this reason that the language was created that best reflected the knowledge already had by the average machine technician. The birth of ladder logic. Ladder diagram was the attempt to translate the relay logic ladder diagrams already known to the average machine technician. It is in essence a wiring diagram that translates simple relay logic to an electronic version of the wiring diagrams in common usage in the United States at the time. Instead of physically connecting relays to form the operating logic of a machine, they were now connected electronically and in essence simulated in a PLC. As with an integrated circuit, the individual physical switches were moved into a single black box. If a control cabinet previously contained a multitude of relays, they could now all be simulated in a single PLC to achieve the same level of logical control. As with most things, there is a downside of ladder logic. Ladder diagram was useful in the days when a PLC was simply a replacement for the logical sequencing of a machine. Since those days, though, machines have been tasked with much more than simple on-off logic. Today's PLCs not only work on logic, but are also being tasked to handle and record data. Additionally, there is a communication outside the machine that must be programmed. If anything can be said to the credit of ladder diagram, it is that it has been able to adapt to these new challenges. To its detriment, however, ladder logic does not teach good practices. Foremost among these is the seeming divide between ladder diagram and pure Boolean logic. Make no mistake, ladder logic is still Boolean at its core. Most technicians do not make the connection between Boolean logic and ladder diagram. There are very few who can speak out a rung of ladder diagram in a Boolean manner. This disconnect is to the detriment of PLC programmers and technicians. The reason for the previous statement is that all computer languages are at their core Boolean logic statements. To understand Boolean logic is the beginning of understanding all computer languages. To understand only ladder diagram, however, is a dead end. Boolean logic basics. There are many facets to Boolean algebra. In fact, if you read the Wikipedia article on Boolean algebra, it can seem quite daunting. In the PLC world, however, we only need to concern ourselves with four basic operations. These are the logical AND, the logical OR, the logical XOR, and the logical NOT. To begin, let's take a look at the logical AND and the logical OR. An AND statement evaluates true if all the variables in the statement are true. If we take, for example, X is true and Y is true, the statement X and Y evaluates out as being true. Conversely, if X equals true and Y equals false, X and Y will evaluate as false. Lastly, if X is false and Y is false, the statement X and Y still evaluates as false. An OR statement evaluates as true if one or both of the variables in the statement are true. If we have X as being true and Y as being true, the statement X or y evaluates as true. This statement, x being true and y being false, and we have x or y, that will still evaluate as true. The statement x being false and y being false, the statement x or y will evaluate as false. As you can see, if only one is true or both are true, the statement will always evaluate as true in an OR statement. Now we have our XOR and our NOT logical operators. XOR is what is called an exclusive OR. This means that only one variable may be true to evaluate as a true statement. So, for example, if x is true and y is true, the statement x or y evaluates as false. That is the case because we can only have one of the two statements as being true. Conversely, x being true and y being false, x or y evaluates as true. Lastly, x being false and y being false, the statement x or y evaluates as false. The NOT statement can also be called an inversion. The NOT statement inverts the state of the variable, or the statement as a whole. In other words, if we have x equals true and y equals true, and our statement is not x and y, the statement will evaluate as false. That is the case because we inverted the value of x with the not statement. So x, even though we began with it being true, is now false, while y, on the other hand, is still true. Following this, the statement, if x is true and y is false, the statement x and not y evaluates as true. Here again, because we inverted the real state of the variable y. The statement x equals false, y equals false, and not, parentheses, x or y, end parentheses, evaluates as true. Note, in this last statement, we inverted the statement as a whole with the parentheses instead of simply one variable. This basically follows the same rules as normal mathematics, with priority given on the parentheses operations. In programming, it's not so important what you think, but how you think. Now we start to bring things together. We will look at this in two ways. In the computer world, you have only variables. In the world of the machine tech, you have contacts and coils. Wouldn't life be much simpler if we spoke one language? Since Boolean logic is the root of ladder diagram, that is, the language that all computers understand, as well as programmers, you can think of Boolean to the programming world as is Latin to the scientific world. It is the common language. So now let's learn how to translate ladder logic. We begin our lesson in translation with a couple of rungs of seemingly nonsensical logic. These two rungs create an always true and an always false bit in temp memory for local use. Let's begin with analyzing network 1. Network 1, the always false. We'll look at this statement from a Boolean logic perspective. The rung creates an always false bit for use in our function. The text next to the graphic indicates how you would logically speak out this rung of code. Note the line through a context simply means that it's inverted or a not. One point to pay special attention to is that any point in the logic, when two or more contacts are in series, this makes it an AND statement. Network 2, always true. We look now at network 2 from the Boolean logic perspective. This rung creates an always true bit for use in our function. The text next to the graphic indicates how you would logically speak out this rung of code. Again, note the line through the contact to signify inversion or a not. Pay special attention to this in that we have parallel contacts. The fact that you have parallel contacts makes it an OR statement. Network 3, the start-stop latch. We now look at a seemingly more complicated example. This example simply combines the elements we learned in the two previous examples. We have two nots inverting two variables, two ands, and an OR. E-stop and stop are in series. Therefore, we know this is an AND statement. We also note that they are inverted using the not. We see start and run are in parallel, so we recognize this as an OR statement. This gives us start or run. Because the two statements run in series, they are joined together with an AND. Thus, we have not e-stop and not stop, and start or run is run. Putting what we've learned into practice. Now that we see how to evaluate a rung of ladder logic as Boolean logic, let's take a look at how we translate this into the other IEC 61131 languages. We will evaluate Network 3 because of its more complex nature. Keep in mind that the examples are mine. As with any computer language, you can usually write it in multiple ways and still come up with the same result. Keep also in mind that the details of the languages are beyond the scope of this presentation. We begin the examples with function block diagram. We begin with the first AND statement. Note the little circles at the inputs. This signifies that the inputs are inverted. So we have the first AND statement, which is and not e-stop and not stop. Below that, you'll see the OR statement. So we have start or run. Both the AND the OR statements are then ANDed together and come out to resolve to the run. Next, we have the structured text language example. We start with an and not e-stop. Then we have and not stop. Then you'll notice the and statement that ties everything together is bracketed in parentheses, or shall I say brackets the or statement in parentheses. So we have or start or run, resolves to run. It's not as complicated as it looks, as the and statement with the parentheses breaks us into two separate parts. So in essence, we have the and not statement ANDed, and then the OR statement isolated in series with the original and nots. Lastly, we have the structured compiled language version. We begin by saying if not e-stop and not stop and start or run, then. And you notice that as with our other examples, we have our two nots in series with the and then we have our OR statement in series with the first ands. Now, if this evaluates as true, our run is going to be true. Due to the nature of the structured compiled language, we will also have to specifically tell it when to go false. So if the statement does not evaluate true, we are going to make and false. This presentation has hopefully shown that although ladder logic has its place and its followers, much better is it to understand it from a Boolean standpoint. Understanding ladder logic in its Boolean form is a big step towards being able to translate it into other languages. Contacts in series are always an AND statement. Contacts in parallel are always an OR statement. The same use of parentheses to signify order of operation in normal algebra applies also to Boolean algebra. As with normal algebra, having the parentheses in the wrong place can affect the result of the equation.